So part 2 of this presentation about electrons, we're going to talk about electron configuration and periodic trends. Electron configuration is a way to assign all the electrons in an atom to a sublevel. And we're going to just start with the lowest, start with our 1s, and work our way up until each electron has a location. So I want to go through an example with sulfur. So let me put sulfur on this periodic table. Sulfur is right here. So there's sulfur. And the regions of the periodic table are the sublevels. And that's why I was telling you, you don't have to remember the capacity because the number of boxes tells you how much. So this area right here is the S region. This area here is the P region. The transition is the D, and these bottom rows are the F. So those are your 4 sublevels, and you can see the number of boxes correspond to that. And I recommend you get out a periodic table and mark it up. Even the stuff from chapter 4, it's a good idea to be marking up your periodic table so you can remember all these things. So here's how we're going to do our electron configuration of sulfur. So sulfur is element number 16. So we have 16 total electrons to mark. And we always start at the first row. So this is 1, 2, 3, 4, 5, etc. on the rows. So we're going to start with the first row, and we've got 1, 2 boxes. So first row, 1, first region, S, superscript of 2, meaning 2 boxes. That brings us to our second row. So our second row, we start with row 2, region S, and there are 2 boxes, 2S2. Then from there, we come over to here. This is the 2P. And this time we have 1, 2, 3, 4, 5, 6 boxes. So now we have 2P6, brings us to end of this row. So now we're on row 3. And we have 3S2, 1, 2. Then we go over here to the 3P, but notice we have 1, 2, 3, 4 boxes. We're stopping at box 4 because that's where sulfur is. And if we add up all these superscripts, we have 2 plus 2 plus 6, there's 10, plus 6, that equals 16. This is called the electron configuration of sulfur. We've assigned every electron to a sublevel. So let's work on some more. Now, if you go back to that previous slide, you'll notice that when you get to the D region, it's always 1 less than the row, okay? So remember, this is our S, this is the P, this is the D region, okay? So let's look at iron, Fe. Okay, iron is right here on the periodic table. It has 26. All right, we're going to start with the very first row. So row 1, we have 2, 1s2. That's the first row. Then we go to the second row. We go to 2s, and there's 2. Then we come over from the 2s over to the 2p, and there's 6 boxes, 2p6. And that gets us to the end of the second row. We go to the third row. We start with 3s. There's 2 in the S region, 3s2. Then we come over here to 3p, and then 6 boxes, so 3p6. That brings us to the end of the 3 row. Now we go to the 4 row, 4s2. Now, here's the first time right here where we hit the D's. So this is D, but it's not 4 because it's always 1 behind. So it's 3D, and we have 1, 2, 3, 4, 5, 6, 3D6. All right, and if you add up all those superscripts, that gets you to the 26. Now, it's getting to be a lot to write, so there's another way to do this called the noble gas shorthand. And what we're going to do is we're going to look at the noble gas before iron. So the one before it would be argon. Okay, you can see it's 18. If we went to krypton, that's too far. And this piece right here, 1s2, 2s2, right through to here, the 3p6, that is argon. So we could write it as square bracket argon, and then we only include the fourth row, 4s2, 3d6. All right, so that's called the noble gas shorthand, and that's a good way to do it too. The next one we want to do is Se. So let's do Se. This time, let's start with the noble gas, okay? So again, argon is the noble gas before. So it's argon. And now we've taken care of everything up to argon. So now we just go to row 4. And we start with 4s, and there's 2. And then this region here, remember that was 3d, and there's 10 of them. And then here, when we're back to the p's, we're back to 4, 4p4. And that's the electron configuration of selenium. And a little bit more on the noble gas shorthand there. So the F block, we don't really need to know it. There's a lot of filling exceptions. Technically, the order is when you're on row 6. So notice in row 6, the numbers go 55, 56, 57, and then that brings you down here, still row 6, to 58. So think about cutting your periodic table and sticking these rows in there, but the paper's not wide enough, okay? And so this takes you all the way to 71, and then you go back up to 72, 73, and so forth, and finish the row. So that's where they come in. And so technically the order is first you fill the 6s, then you go down to the 4f, then you come back up to the 5d, and finish off with the 6p. But there are many exceptions, and you notice right here, 57, one went in the 5d before it went in the 4f. And they kind of go back and forth. So I'm not going to ask you those because they're tricky and there's a lot of exceptions. But if you want to just do some for completeness, you can see how that works. So this shows all those exceptions. You can see that the red is the predicted using always 1 in the 5D. The black is the actual. And you can see that actually more commonly, there's not 1 in the 5D. So they're kind of tricky. I won't ask you those on tests. So let's do a couple more electron configurations. Let's do aluminum and bromine, okay? So Al, notice it is right here, all right? And I recommend you pause it here and you try these and then turn it back on. So Al will always start with 1s. Actually, yeah, let's start with 1s. I was going to do the noble gas. We'll do both. 1s2, then we go to row 2, 2s2, and then over here, 2p6. That takes care of the second row. Then we go to the third row, 3s2, and then come here, 3p1. Or, using the noble gas before it is neon. So we'll do neon, and then just the 3 row. 3s2, 3p1. All right, that's aluminum. Let's look at bromine. So here's bromine. Let's do the noble gas. So the noble gas before it, argon. And then we do the row that bromine is on. That's row 4. So 4s2. And then we do 3d10, because remember, here's the 3d. And then we come back here to 4p, and we have 1, 2, 3, 4, 5, 4p, 5. Okay, and so that is bromine. And then lead, I wouldn't really ask you this because it's going to have F's, but let's go ahead and do it. Here's lead. So we'll do the noble gas before it, which is xenon. So xenon. So we just do the row lead is on, that's row 6. So we'll do 6s2. And here's where those F's come in. The F's are 2 behind. So on row 6, these are actually 4F. On row 7, they're actually 5F. Okay? So it's 4F, and there's 14 boxes, if you count them over. Then that brings us up to the D here. So then that's 5D, and there's 10 boxes. And then we go back to the P, which is 6P2. So there's some examples of electron configurations. Okay, notice you don't have to memorize the electrons in the sublevels because you can just count the boxes in the block. So we can use electron configuration to look at valence electrons versus core electrons, okay? So the valence electrons are the outermost principal shell. So these electrons are important because they're the ones involved in chemical bonding. And so you can see them, if in this case 3 is your highest level, so it's really just the S and the P, because if you have D's, they're going to be the level before, so they'll be core. So the S and the P give you your valence electrons. Silicon has 4 valence electrons because they're the ones in the 3 level. And it has 10 core electrons. And so that 4 valence electrons, now we have a couple of ways of getting at that. That's the number on top of the column as well. And it's the outermost electrons. And for this element, selenium, the D's are also core electrons. Let's look at how electron configuration fits in with ions, okay? We talked a little bit about ions, that metals will lose electrons, nonmetals will gain electrons, and the goal is to look like the closest noble gas. So let's look at first calcium. Let's think about its electron configuration and what would it do if it became an ion. So here's calcium right here, okay? If we did the noble gas shorthand, it would be argon and then 4s2. That's calcium. Well, if calcium becomes an ion, it's going to want to look like a noble gas. And since it's a metal, metals lose electrons. So how many is it going to lose? Well, 2 is the number, so it can look like argon. So calcium is going to become a +2 ion, and that electron configuration is going to be the configuration of argon. All right? So ions will look like a noble gas, and that's true of magnesium, and it's true of strontium. All the elements in that column will lose 2 electrons and look like the noble gas before them. Let's look at nitrogen. Here's nitrogen. Okay, so if we did its electron configuration, we could do the noble gas before, which is helium, but that's also, we could just say 1s2. And then 2s2, 2p3. So that's nitrogen. Well, nitrogen is a nonmetal, and nonmetals gain. So how many does it want to gain? Well, it's going to want to look like neon. And so that means 1, 2, 3. So instead of being 2p3, it's going to be 2p6. So that is the configuration, of neon. So nitrogen is going to be nitrogen, so now it's nitrogen with a 3- charge, is going to have the same electron configuration as neon. All right, what about iodine? You try it first and then turn the video back on. So iodine without a charge is Kr, the noble gas before it, and then we do row 5, 5s2, 4d10, 5p, 1, 2, 3, 4, 5, 5p5. So what do you think iodine is going to do to become an ion? Well, can you see that if it gained one more, it would look like xenon? So instead of calling this a 5, we'll make it a 6. The charge will be negative, and now it will look like, it looks like it turned into an 8. Now it looks like, sorry, I did too many square brackets, it's xenon. We only need one of those brackets. Okay, so we can do the configuration of an element or an ion, and the ions will always look like a noble gas. So this slide shows those same ions that we just did, plus it shows a lot more of the elements and the ions that they form. And we'll talk more about this in Chapter 5 when we talk about naming compounds. But notice that these elements here, the transition elements, most of them have more than one possible charge, and that makes them a little bit more complicated, but it's because they have those d electrons that makes them a little bit more complicated. So we'll talk more about those. There's a few trends of the periodic table that are important to remember. And the first one is atomic size. And this is radius or volume. It's not mass, because we've already, the mass, they just get bigger as you go across and down. And there's a nice figure of this in your book that I recommend you look at. But the trend is that they get smaller going across. And they get bigger going down. And so going down makes good sense as you're adding another shell for the electrons, they're getting bigger in mass, so as you go down the column they get bigger. The smaller across maybe isn't obvious, but what's happening is you're adding more electrons, you're adding more protons, but you're not adding additional space for them to be in. And so what happens is those additional protons just pull the whole thing tighter together. So that's the trend, that they get smaller going across, bigger going down. The next trend is in ionization energy. So ionization energy is the energy it takes to remove an electron, okay? And this is the reverse trend. So going down, it gets smaller. And the reason for that is that as you go down, the electrons are farther from the nucleus, it's easier to remove them. It takes less energy. And going across, it gets bigger. And the reason for that trend is as you go across, you're adding more and more electrons. It goes that you don't want to lose them anymore, you'd rather gain. So these 1-8 columns, they want to lose their electrons, so they lose them pretty easy. And as you go across, there's more electrons. They tend to want to gain electrons instead of lose them. So that's the trend. Smaller going down, bigger going across, the reverse of the size. And the last trend is metallic character. And this really follows right along with the ionization energy, that the one that's the easiest to lose an electron is the most metallic. So down here in this corner is the most metallic. And up here in this corner is the least. And that follows the non-metal-metal dividing line. More metal this way, less metal this way. And that brings us to essential skills. Know the energy levels and the sublevels, list them in order from the lowest to highest energy, write electron configurations for atoms and for ions. And on tests, I won't ask you F, a sublevel. Identify valence electrons and use this to predict ion formation. And there's a lot of ways to identify those valence electrons just from the periodic table, from the electron configuration, and use periodic trends in radius, ionization, and metallic character. So be able to identify which would be the most metallic, least, which is the biggest, smallest, etc.